All right. So initial angular velocity of a rotating body is 21 radians per second. Body's rotation accelerates at a constant rate of 1 radian per second squared for 15 seconds. How many revolutions does it make in that time? Revolution is obviously one full turn, one full circle. Okay, I'll give people another 30 seconds. So remember, these angular acceleration problems are just like the regular acceleration problems. It's no different. The only maybe a little wrinkle is we're asking for revolutions at the end.
So one revolution, one goes all the way around.
Right. So everybody made a choice? No? Okay, give another 15 seconds.
There are 2 pi radians.
Okay, let's close it up so we can do more problems later. Let's see what people have said. Okay, a lot of people say E. There's a bit of a spread though. Okay, so let's take a look. What do we know? We know the time, delta t. Delta t is 15 seconds. We know the initial angular velocity. Okay, remember, what was the symbol we used for angular velocity? Yeah, the thing that looks like the curly W sigma. Okay, omega 0 for the initial, that's the way I like to write it. And that's 21 radians per second. Okay, what's the symbol we use for angular acceleration?
Alpha.
Yeah, right, that's the alpha. All right, now, by the way, because we usually introduce angular acceleration and centrifugal acceleration at the same time, or the same lecture, very often students get those mixed up. So is everybody clear on the difference between centrifugal acceleration and angular acceleration? If that's unclear, then you don't know either one of those probably very well. Okay, so that is going to be very clear. So So centrifugal acceleration is when we have constant speed going around a circle. And then there's this acceleration because the velocity vector keeps changing. There's an acceleration that pulls you towards the center of the circle, and it has a magnitude v squared over r. Okay? Centrifugal acceleration is about constant speed around a circle, pulls you into the center. Angular acceleration is completely different. It's when something's rotating, and if it gets faster, it has an angular acceleration. If it gets slower, it has a negative angular acceleration. Now, in your homework, by the way, I didn't really mention this when I was doing a lecture, but in your homework, there's a convention in terms of rotations that as you look at something rotating, if it's counterclockwise, if it's opposite to the way the clock goes, if the clock goes this way, the hand goes this way. If it goes the other direction, it's considered positive. If it goes the way the clock goes, it's considered negative. It's the same way we measure angles from the x-axis. It's measured counterclockwise and the positive x-axis. And that's sometimes a convention. Most people use it. All right. Now we want to know the change. Yeah, question. Okay, so that's a great question. If an object is speeding, suppose an object is going around like this and getting faster. Okay, there's still centrifugal acceleration. Like, look at the end of lecture last time, right? We did all these problems. If it's constant, we had centrifugal acceleration going v squared over r. If it was getting faster, we also had v squared over r, but we also had the tangential acceleration. So there was two pieces. If it was slowing down, there was centrifugal acceleration still going towards the center, but we had the tangential acceleration going back. Okay. So there's always centrifugal acceleration when you're going around the circle. All right, but this has nothing to do with that. This is the angular acceleration problem. Okay, this is the alpha thing, and so we want the change in the angle or the change in the delta theta. And so we have 1/2 alpha delta t squared. This is the formula that will get us the answer in one step. Omega naught times delta t, and then we put in 1/2 times alpha is 1.0 radians per second squared. Delta t is 15, square that, plus the initial angular velocities, which is 21, times 15, and that comes out to 428 radians. And notice this was a mean problem in that if you were lazy and didn't want to, or not lazy, but you forgot to convert it to revolutions. I don't know anybody lazy that would just stop intentionally a problem to get a wrong answer. But if you forgot to convert it to revolutions, then there's a nice wrong answer waiting there for you. But we want to convert this into revolutions. So what do we have? We know that 2 pi radians is equal to 1 circle around, so 1 revolution. Okay. And so 1 radian would be 1 over 2 pi revolutions. And so we'll put that in 428 over 2 pi revolutions. And that comes out to about 68 revolutions. Okay? Are there any questions about this? That's recording. It's fine. Everybody's okay with that? All right. Let's do another one with angles. I noticed I didn't really do enough examples in the lecture, so I want to fill in the gap. Okay, rather than redrawing it, let me use the drawing I already have in my notes and be lazy. Okay, so the next problem, we have a plot of angular acceleration alpha in radians per second squared versus time in seconds. And if the initial angular velocity at t equals to 1 second is 15 radians per second, initial angular velocity, what is the angular velocity at 4 seconds? Okay. So let me open up the poll. Oh, no, you need the choices, I guess. So for the okay, so the problem is if you can see the problem, you can't see the choices. So let me write it up here. So A is 21 radians per second. B is 15 radians per second. C is 42 radians per second. D is 6 radians per second, and E is 32 radians per second. Okay. I will open up the polling now. Yeah, so it's not just getting faster, but the amount of getting faster gets faster. So it's like yeah, it's not a parabola, but it's like something to the third power at one time. Yeah. There's names which I don't remember. There's names for all these things like jerk and thrust and all these things. Yeah.
Jerk is the one above acceleration. I don't know the one above.
Yeah. Okay. By the way, I had a question about the calculator thing. That I know somebody else in the help had the same issue. When you divide by 2 pi, and then your calculator you write division sign and you write 2 pi, you're not dividing by 2 pi. You're dividing by 2 and you're multiplying by pi. Okay? If you want to divide by 2 pi, you have to put parentheses around 2 pi. And that's kind of annoying to have to type so many things. Just remember 2 pi is 6.28. Anyways, let's see. All right, anybody had to make a choice on this? Good. I'll give you another 30 seconds. Okay, if you haven't had a chance to chime in, go ahead now. Let's see what people have said. Okay, nice little distribution here with the Tika A. All right, so remember, this is just like straight line stuff with acceleration and velocity. Acceleration is the derivative of the velocity. So go in the other direction. The integral of the acceleration is the angular velocity. So we do this for the angles as well. It works just fine. The derivative of the angular velocity is the angular acceleration. The integral of the angular velocity gives you the change in the angular acceleration. Everybody's good with that? Okay. So once again, I'm going to be lazy because I have a nice drawing right here. Okay. So we're going to calculate the integral of the angular acceleration. That will give us the change in the angular velocity. Okay? So we have triangles. And we have here, this triangle has a base of 1 second, has a height of 3 radians per second squared. So 1/2 times the base times the height. And that's 1.5. Okay. And then we have a rectangle here with a base of 1 second, height of 3 radians per second squared. That gives me area of 3. And then I have another triangle with a base of 1 and a height of 3. And that gives 1.5. So I add up the areas together. They're all positive, so they all come with plus signs. 1.5 plus 3 plus 1.5 gives me 6 radians per second. And then, once again, there was the evil choice that if you just put down 6, that would be wrong. You have to add this to the initial angular velocity, and that gives you 15 plus 6, so that's 21 radians per second. Okay, any questions about this problem? Yeah. Oh, okay. The thing is, if you assume it's a trapezoid, you still get the right answer because the area will come out the same. It is a trapezoid. Yeah. But you got a different answer. Okay, but then you probably made a mistake in some of the calculation. So the area for the trapezoid, the area for a trapezoid, is you take the average of the top and the bottom, and then you multiply by the height. And so, sorry? No. Yeah. So for a trapezoid to work, it has to work for a rectangle because a rectangle is a special case of a trapezoid. And so a rectangle is just base times height. There's no dividing by 2. The averaging has a dividing by 2 by adding the top and bottom dividing. Okay. Other questions? All right. So I was thinking about which other problems to go through. Would you like to take a look at? So we have many questions. We could go through some problems in the practice quiz. Is that what you'd like to do? Yeah. No. Okay. Some people say no. Or we could go through practice problems on the list of practice problems, or we could do a couple of these, because I'm feeling if I have to play them, there'd be people in all different directions. Okay, let's see. Let's do. Okay, let's do number 1 on the practice quiz. And then we'll do one of the practice problem things. Okay, all right. We'll do this together. A boat crossing a 149 meter wide river is directed so that it will cross the river as quickly as possible. And the boat has a speed of 5.5 meters per second in still water, and the river flows uniformly at 3.30 meters per second. So you see the picture of the current going to the right. We want to cross the river, which is basically we need to move vertically. Okay. So calculate the total distance the boat will travel to reach the opposite shore. Right. So before I go through the solution, why don't you give it a few minutes? I'll give you a few minutes to try, for you guys to try it yourself, and we'll go over the solution. It's not a perfect question, but I don't like just giving a solution without having to try it. Okay, yeah, it's not a clicking question, so I didn't. You don't have to use it. Okay, so first of all, let's ask the question: which way should the boat be directed? Straight ahead. Yeah, everybody agree? Okay. If you don't go straight ahead, you lengthen the time it takes to cross the river. So the first part was uh, you want to cross the river as quickly as possible. So it's only the vertical component. Well, okay, it's not really vertical. The page is displayed vertically. It's really the perpendicular to the river that you're trying to get the largest velocity. Okay. People have enough time to get pretty much done, or close to being done. All right. All right. If you're still working, go ahead and keep working, but I'll start cranking up the solution. Okay. So only the y component matters. So let me draw x and y first of all before I say that. So I have y in this direction and x in this direction, plus y plus x like that. Okay, so only the y component matters in terms of the time to cross the river. Okay, only the y component matters. So the boat should be directed directly across. In other words, the boat should just try to go, should point in this direction. Okay? It won't go in that direction because the river is going to push it away, but that's the way it should be pointing. Okay, so now if we're going to look at the y component of the boat's velocity, the river doesn't matter because it's only flowing horizontally. So to get the time, we just take the distance divided by the speed. Okay, everybody's good on that? Or delta y or something, whatever you want to call that. So it's 149 meters divided by the speed. We're talking about the y component, so 5.50 meters per second. Right. Is there anybody confused about these steps here? Everybody's good? So we're talking about, this is the change in the delta y, how far is across like this, and this is actually it's the y component of the velocity that I'm talking about. Okay? All right, so now, by the way, in case you have trouble writing down equations like this just from scratch, like delta t is equal to distance over speed, if you can't remember if it's the other way around or there's some other combination, let me just tell you how I remember it. I know there's a relationship between distance, velocity, and time, but my memory is kind of not that great, but I can remember there is some relationship there. And now, if I'm going to write down a formula for time, I know that it has units of seconds. So I need to take distance and speed and get a combination that gives me something with units of seconds. And that's enough to remind me that it must be distance over speed. Is everybody good on that? Does that help you? Okay, so, all right. That's how I remember these things. And so 149 divided by 5.50 is 27.1 seconds. All right, so that gives us the time. But we want to know how far does it travel in total distance, the boat does. Okay, and so we need to know how much it drifts in the x direction. We know the y direction, the delta y, we had that before. But delta x, that's how much it will drift. Delta x will be the speed of the river, which is, oh, so thank you. Very good. 3.30 meters per second, and times the, I'm really zoomed in, I've forgotten how close I am. That's why it's hard to see on the page. Times the time, 27.1 seconds, okay? And so that comes out to 89.4 meters. And so the total distance will be equal to sum of the squares, delta x squared plus delta y squared, and plug in the values. Let me zoom out because it's really hard to write in that range. Okay, and so it comes the square root of 89.4 plus 149 squared. And so that comes out to 174 meters. Okay, any questions about this? That's good. All right. Let's change it up. Since some people didn't want to do the practice quiz, let's now do one from the practice problems I've put up. And to do that, I want to do, if I put it on the screen, it doesn't go onto the camera. So let's do it from I'll view it from my phone and write it here. Okay, so this is coming from the projectile practice problems, right? So if you're not clear on where this is coming from, you go to D2L, and there's lecture material here, the practice quizzes are here, but then I also have these practice problems, and then there's a bunch of problems you can do. Practice problems, practice projectile problems, that's where this is coming from, okay? All right, so the problem is, it's about a football. So a football I just realized you could probably even see like this. Yeah, okay, so I'll just write it this way. A football is kicked from the ground with a speed of 40 meters per second at an angle of 45 degrees above the ground, which is, okay, if we say ground, we assume it's horizontal unless we say something about having an angle. Okay, the three parts we'll do, this may take us to the, I don't know how long it will take us. Let's see how long it will take us. Questions are, how long is it in the air? Okay, and how high vertically does it go? And the other question is, how far does the ball travel horizontally? Okay, we'll let you do a little bit of work on it, and then we'll go through the solutions of each. so remember the steps that I laid out for projectile problem. First step, get the components of the initial velocity, the x and the y components. Then the next step after that, figure out which direction determines the time, the delta t. Then solve those equations for that direction, either x or y. And then go to the other set of equations. Okay, I think I probably should start the solution now so that I don't keep you too late. All right, so the first step is to get the components of the initial velocity. Okay, so v0 is like this, and let's say this is positive y, and this is positive x. So we have v0x, and we have the v0y. Okay, and the angle is 45 degrees. All right, so v0x goes with, it's the adjacent side. Well, 45 degrees is sort of mistake-proof. You can get them wrong, it doesn't matter. Okay, so v0x is 40. Okay, that was up here, this speed. Okay, 40 meters per second initial. Okay, let's straighten this up. Times the cosine of 45 degrees, and that comes up to 28.3 meters per second. V0y is 40 meters per second times the sine of 45 degrees, and that comes out also to 28.3 meters per second. Okay, because 45 is the same as 90 minus 45 is 20%, exactly the same. Okay, now we want to know what determines how long it's in the air. The horizontal stuff doesn't really matter at all. Okay, it's going to go up and it's going to go down. When it goes down, the clock stops. Okay, so we can look at the y motion for this. So we're going to look at the y motion to figure out the time. And by the way, for those of you who like shortcuts, being lazy, getting at it quickly, if the problem is that it goes from some surface, comes up and goes back down, there's a shortcut for getting the time. You can take the time it takes to drop from the top to the bottom and multiply by 2. Because it's not equal. It takes the same amount of time to get to the top as it does to get to the top of the bottom. Okay? Everybody do that? If it's a more complicated problem, like a projectile, it's shot from here and then it falls to the ground, that trick's not going to work. But if it goes from the ground, comes back to the ground, you can take the time from the top to the bottom and multiply by 2. However, I'm not going to do it that way because I'd rather just show you the straightforward way, which is the way most people will do it. Okay, so we will, and then we will, okay, there we go. So we have y minus y0 is equal to 1/2 ay delta t squared. You guys remember doing this. d0y delta t. Okay, just like we did for the angular acceleration stuff, this is the actual acceleration stuff. So y minus y0 is 0. It starts and ends at the same place. Okay, in terms of the y direction, the y position. And then we have 1/2 negative 9.8 meters per second squared delta t squared plus v0y, which is 28.3 times delta t. Okay, here, because we have 0 on this side, we don't have to do the quadratic equation. We could use the quadratic equation, but we can just divide by delta t. So I'm going to divide by delta t, and then I have minus, I'm going to simplify this to minus 4.9. There's only a delta t left here, 28.3. Okay, just divide delta t. And so delta t gives, you solve for delta t, you get 5.78 seconds. So that's the first part. Questions about this? Everybody's good? Okay, now we want to know how high it goes vertically. Oops, that's no good. So we have to, okay, I can't really show this. I don't have space here. So now we want to know how high it goes vertically. And I lost my phone here. So just 1 second. Crashed on me. Okay, to get how high it goes vertically, we can simply say, all right, let's say the initial time is at the bottom, but let's say the final time now will be at the top. Okay, because then we can calculate y minus y0. All right, so in this case, if we can use various things. We can use vy squared minus v0y squared is equal to 2 times ay y minus y0. Since we know delta t, we could have used another formula, but that's what I'll use here. At the top, we know that vy is equal to 0. That's when it peaks. So the y velocity will be 0. So we'll have 0 squared minus 28.3 squared is equal to 2 times negative 9.8, which is the acceleration, ay, times y minus y0. And then I can now simplify here. This obviously goes away, and we solve for 1 minus y0. Comes out to 40.9 meters. Okay. Any questions about that? Last part was how far does it go horizontally? So for horizontally, we look at the x motion. And here we knew the delta t. We found that delta t was 5.78 seconds. So to go x minus x0, there's no acceleration here, just v0x delta t, just a constant velocity problem. And so v0x, we found that on the previous sheet was 28.3. So 28.3 times 5.78, and that comes out to 164 meters. Okay. Any questions about any steps of that problem? All right. If not, You guys on Monday,